Welcome aspiring and other aviators to episode 4 of the Blue Skies Private Pilot Crash Course, where we'll be going over the flight instruments in an airplane. At the end of the video, you will know all the instruments most planes in the US are equipped with, from Cessnas to Airbuses. They don't change too much, and exactly how they all work. Now, I remember my first time looking into a cockpit of an aircraft and seeing all the knobs, all the clocks and instruments. It was severely intimidating, not only because it looked like this, but I also looked like this. I was just learning how to read clocks, much less vertical speed indicators, and if that little guy can do it, so can you. And don't worry, the cockpit you're expected to understand is going to look a little bit more simple, a little bit more like this, so much simpler. And I'm here to explain to you each instrument and how each one works in detail. So let's get started with what you're most familiar with. The magnetic compass is one of the oldest and most reliable navigational instruments man has ever created. And today, every airplane has to have one. If you didn't know, a magnetic compass works off of the principle that the Earth has a magnetic north that is so strong, a magnet will feel attraction to it across the globe. So as long as you are holding a magnetic object, a magnetic compass's magnetic needle will always be pulled towards magnetic north. Slap on the reference line and you will have a magnetic compass that you can read in an airplane. There are a few errors that you need to be aware of in this instrument though to navigate effectively. Also known as gyroscopic instruments, as the name implies, these three instruments take advantage of gyroscopes to accomplish their mission of giving the pilot information on the heading, the attitude, and coordination in flight. Gyroscopes have a very useful property in the aviation field, and this property is called rigidity in space. This is the same property that keeps a top vertical while spinning. When you spin it, it keeps spinning and doesn't easily change direction. Now, a gyroscope is just a fancy version of a spinning top. It has a spinning wheel inside of it that can freely rotate in any direction. When the gyroscope is set in motion, the spinning wheel creates a kind of spin force that wants to keep the gyroscope spinning in the same direction. Just like this, it doesn't really want to tip over like when you spin it. This spin force is what gives gyroscopes their special ability. If you try to tilt or move the gyroscope, it pushes back in the opposite direction to resist the change. It's like it has a mind of its own, wanting to stay in its original position. This ability of a gyroscope to resist changes in its orientation is called rigidity in space, meaning the gyroscope's spinning wheel wants to stay in a fixed same direction, no matter how the rest of the world or plane is moving around it. All these instruments have their own spinning gyroscopes powered by either the electrical system or a vacuum air pump spun by the engine. If there is an issue with these instruments not working, it can be usually attributed to the vacuum air pump providing insufficient air pressure to the gyros. The gyros are then connected to the interface by lights and delicate rods to detect small changes in the force being applied by the gyro. The first one we're going to be going over is the heading indicator, which is the first part of the six-pack we will check out. This looks exactly like a compass from the top down, plus an airplane, and it acts exactly how a magnetic compass should act without all of the magnetic flaws in the compass. You can see that the pilot was on a heading of 90 degrees when they were flying, and it is important to set the heading indicator to match the magnetic compass using the knob found on the bottom left of every single heading indicator. For every flight, you need to go ahead and use that to maintain accuracy. If your heading isn't put in correctly, it can be a maximum of 180 degrees off in flight, which is very bad. But how could it even get that bad? Well, I'm glad you asked. The heading indicator and all the rest of these instruments are only accurate when the plane is running. It's only working when they're running. Since the gyroscopes also turn off the plane, if you turn off the plane on the ground at a heading of 60 degrees, or 90 degrees in this case, someone moves your plane over to make room for their Rolls Royce. Let's just go ahead and use this example right now. My Rolls Royce has not come in yet. So let's just act like this is a Rolls Royce. When we have the plane right here at a setting of 90 degrees, we're gonna go ahead and turn it off. The gyroscope in this actual indicator is going to be turned off and it's going to be stuck on 90 degrees. Here's little Warren Buffett with his Rolls Royce. I don't even know if he has a Rolls Royce, but he wants to park his plane right there. His Rolls Royce right there. He's gonna go ahead and tow it and move it to a heading of 360. Move his Rolls Royce right there. Next time you turn on the plane, it is going to be saying that the heading is here, but you're actually headed right there. So that can be absolutely detrimental in a variety of different flights. I really wish my Rolls Royce came in. But when you go back to flying, the heading indicator will still be at 90 degrees. Can you tell I've made this mistake before? The second part of the six-pack is located at the bottom left or the top right in this drawing, and it is going to be the turn indicator, which indicates the direction of roll, the rate of turn and slip. So it's going to indicate the rate and direction of roll, which is on the long way, how you're going to be turning, just like this as a little reminder, remember that from episode 1. And any slip, which is nose outside of a turn, or any skid pointing into a turn, and all that indication, which is considered the yaw of an airplane. The roll is clear to see from the instrument as the little plane rolls left or right. So does the big one you are sitting in, laying in, or standing in. The rate of turn is indicated by the little white tabs on the left and to the right. If you ever forget, there's a little L and there's a little R. The wingtip on either side is in line with the lower white tab. You are making a standard rate of turn, and the standard rate of turn is 3 degrees per second or 180 degrees per minute, meaning if you were stuck in a cloud while flying and you really don't want to be in that cloud and need to turn around to get out of it, look at your watch and this instrument. Make a standard rate of turn to either side until the wing is in line with the white tab. Wait 1 minute to go back straight and level flight, and you will find your way out of the clouds soon enough. Or you could just use your heading indicator, that works too. The slip or skid indicator is on the bottom of the instrument. It's also called the inclinometer. That's a very weird word to say and no one ever uses it, but it's also called that. This measures the yaw of the airplane, which is the orientation of the plane in respect to the vertical axis, just like we talked about in episode 1. When the little ball is on the left side of the plane, so this little black knob is actually a ball that can move a little bit to the left or move a little bit to the right. This just indicates that the tail is either to the left or to the right. When the ball is in the center of the two black lines, then your nose and tail are pointed in the direction of the turn and you're considered coordinated. If the little black ball is moving to the left or to the right, you are in an uncoordinated turn. To fix this, you will step on the ball. That is, push your foot on the rudder pedal at your feet on the side that the black ball is moving towards. This moves the rudder, typically the vertical control surface on the empennage, in the direction you are stepping in, effectively adjusting the yaw of the airplane before it becomes an issue. The instrument's vacuum or electrical system is usually running separately from the rest of the gyros, typically electrically too, to make sure you at least have this instrument in the case of the main vacuum pump's failure. The last gyroscopic instrument we are going to go over is the attitude indicator, or the artificial horizon. It shows banking aviation just like how the turn indicator does, and how high or low the nose of the plane is pointing, aka pitch information. The banking information is displayed with the white lines. They're black here, but it's a white board, and an arrow at the top of the instrument. Each line symbolizes 10 degrees to the left or to the right in roll, and a skip to 60 degrees right over here. The pitch is displayed as the artificial airplane in the middle that can be adjusted with a knob on the bottom that I did not draw in as well. That's basically the knob, and the degree pitch lines above and below the artificial plane. I'm not sure why they really call it an artificial plane anyways. I mean, aren't all planes artificial? Oh well. The last important bits of information you need to know is it is always blue over brown, or black, it depends on each indicator, but blue is always going to be on top. Just so you know. Bam. That means that the blue, or the artificial sky, is always meant to be on top of the brown, which is the artificial ground. It may sound simple, and what situation would ever make that information useful ever? Well, I'm glad you asked, you thoughtful student, you. It is when you have no reference to the horizon anymore, like in a cloud or during a dark night where the horizon blends in with the sky. That's when it's very useful. The last three instruments that we're going to be going into detail, and we are going to be going into a lot of detail on these ones. In the standard six-pack are the vertical speed indicator, which is the VSI, the altimeter, you don't have to shrink that, and the airspeed indicator, or the ASI. These are all made possible by the Pitot-Static system in the aircraft. To understand how the system works, you have to understand the two different parts, the pitot and the static ports. The static port is found either on the flush side of the aircraft, which on this little guy, it's going to be like right about here. It's going to capture non-moving air to measure atmospheric pressure at all times. Measuring atmospheric pressure is constantly important because it has many variables it can change with, including air temperature and elevation. So on long cross-country training flights with lots of changes in these specific variables, atmospheric pressure can be changing every minute. All three instruments, the altimeter, the vertical speed indicator, and the airspeed indicator again, use the static source to constantly check the atmospheric pressure to allow for instant and accurate instrument readings at all times. And then we have the pitot part of the pitot-static system. The pitot tube is located typically on the left wing of training airplanes, pointed forward to capture ram air. Ram air is the air that the airplane comes into contact with while in motion. I remember it as the air that the plane rams into. Yeah. This air is higher pressure than the static air and only increases with pressure the faster the aircraft is moving through the air. The only instrument that takes advantage of this tube is the all-important airspeed indicator, and this is all going to make a little bit more sense soon. So yeah, pitot-static system, let's go. Let's start with the vertical speed indicator, and it just does what the name says. It tells you how fast you're ascending or descending in feet per minute. It works by taking the static air and feeding it into the capsule, into a capsule, also known as a diaphragm, in the instrument, and then second is going to be taking it outside the capsule, be it a small calibrated leak. The inside of the capsule will have the air pressure for the current static air that is coming from the static port, and the outside of the capsule is going to have a 3-second delay of the air pressure from about 3 seconds ago. So the capsule will then expand or contract if the outside air pressure is higher or lower pressure, and the instrument will display the expansion and contractions as a reading on the face of the instrument in feet per minute. It is important to note that the instrument has a small lag, considering there is a small calibrated leak, for comparing the air pressure of right now versus about 3 to 5 seconds ago. So if you happen to climb a couple hundred feet, you will be in an area of lower pressure now than you were 3 seconds ago. This would then make the diaphragm expand a little bit and indicate a climb on the instrument base. The two flaws with this instrument, again, are just that it is a delayed instrument, which is not very good, and it relies solely on the static tube to feed it air. If the static tube is clogged, then it would read 0 or get stuck at the last indication, no matter what your vertical speed is. At a certain point in the last 100 years, pilots found out the hard way that if we fly too high in the air will get too thin to breathe, and thus we would fall out of the sky. Thus we invented the altimeter, because carrying an 18,000 foot ruler was just too heavy. The altimeter will become one of the most used instruments in your flight training, and we will be going over it for a good minute so that you know exactly what you're talking about when you take all of your exams. The altimeter's job is to measure the difference in altitude between you and sea level, effectively telling you how high you are. It accomplishes this in a similar way to the vertical speed indicator, except no calibrated leak. So what's going to happen is there's the static port right over here, which is going to be filling the diaphragm with static air, and then there is going to be the diaphragm, which is covered in air similar to sea level air pressure, that is. So there's going to be one air pressure outside of the diaphragm, then there's going to be another air pressure inside the diaphragm. So the actual diaphragm is going to be expanding or contracting according to the actual air densities, giving you an actual altimeter reading. To read it, you will look at it just like hands on a clock. The smaller hands read bigger increments, and the bigger hands read the smaller increments. The smallest hand is going to count as 10,000 feet above sea level, just like the hour hand would. The middle hand is going to be middle length, and it is going to be 1,000 feet above sea level, just like the middle hand or the minute hand. And the longest hand is going to be 100 feet above sea level, just like the seconds hand. I'm gonna go ahead and make an example real quick. So looking at this example now, we can remember that the small hand means 10,000 feet. We can see that the middle hand means 1,000 feet, and then the longest means hundreds of feet. So since it just passed 1, that's 10,000 feet. It just passed 4, we could say that's 4,000 feet. So 10,000 plus 4,000 equals 14,000, plus the 5 longest hand times 100, that is going to be 500 feet. So 14,500 feet. Pretty easy. And the main issue we could see with the altimeter, other than the fact that it is not a great drawing, the main issue is the same that the vertical speed indicator had, which is if the static port is clogged, then the altimeter will stay stuck at an altitude reading no matter the change in altitude. And look at this. This is a great time to talk about the different types of altitude. You may notice there are some tiny numbers right over here that don't really seem to mean anything. That little window right here in an actual altimeter would be called the Kalsman window. And that number in there is called the altimeter setting and will be typically provided to you from air traffic control or ATIS, the Automatic Terminal Information Service. More on all of that stuff later. In this Kalsman window, you must adjust it accordingly to the current setting to get an accurate above sea level reading at all times. Since, as we went over before, atmospheric pressure can be constantly changing. The altimeter setting is an adjustment to the altimeter. You make sure so that you're actually reading accurate height, and therefore absolute altitude will be shown no matter where you go. If you do not correct the altimeter setting on a long flight, you could, for example, be expecting to be at 3,000 feet above the ground, but you're really at 1,000 feet above the ground, much less room for error and a ton of other legal issues. You might also be thinking, Brad, why would the altimeter even bother to tell me the altitude above sea level when I have to adjust it all the time? Thank you. Oh, wait, you have another question. Awesome. Why can't it just tell me my altitude above ground level? I don't even fly anywhere near the ocean. First off, thank you so much for both of those questions. I always fly near the beach, so I can't really relate. But you do bring up a good point. The reason we use above sea level so often is because above ground level changes so much more often. You know, mountains and stuff. And it is less consistent, while sea level is an average that we all can agree on. Let me get a new whiteboard for you guys so that I can just go ahead and talk to you about different types of altitude. Just drew that. Look at that little mountain and then the above ground level. So neat. There are other altitudes that you will need to know to stay safe and to ace your exams. So there is also indicated altitude, which is exactly how it sounds. It is whatever your altimeter indicates with no corrections for non-standard atmospheric conditions. And it is also good to remember that standard conditions are about 59 degrees Fahrenheit, as well as 29.92 Hg at sea level, which is inches of mercury. We'll get into that a little bit more. So to get the above sea level from indicated altitude, you adjust for non-standard conditions unless you are living a standard day. Then you can take above sea level and take it to above ground level by just subtracting the ground's elevation. So if you're actually at 1,000 feet above sea level and then there's a 500-foot mountain, you're only 500 feet above the ground. There is then pressure altitude that is useful for flights over 18,000 feet. There's a little drawing real quick. So you could just remember indicated altitude corrected for all the non-standard days and everything is going to be above sea level, which is the true altitude. We can go ahead and subtract the ground elevation so that we can get above ground level. And then we're going to be getting into pressure altitude, which is PA for short. Again, useful for flights over 18,000 feet and testing aircraft performance. Pressure altitude is the altitude above the theoretical plane where atmospheric pressure is the standard 29.92 inches of mercury. To calculate pressure altitude on the ground the long way, you get the altimeter setting and you input it to your altimeter to get the indicated altitude. A little complicated, but it is way easier to do in flight. You then take the altimeter setting to get the difference between that and standard altimeter setting, which is 29.92 inches mercury. You multiply it by 1,000 feet, or 1,000, because each Hg is equal to 1,000 feet in difference to get the altimeter correction. So if you want to put it into a little bit of an equation, the altitude correction is equal to the current altitude setting, CAS, minus the standard altimeter setting, which is 29.92 again. We can put these in little brackets or parentheses, and then you multiply it by 1,000 because again, each inch of mercury is equal to a 1,000 foot difference. And if we plugged everything in, then you would take your indicated altitude and subtract your correction to get your pressure altitude. That's a lot of things right there, but I promise you, once you do some examples, that will just fix everything. So let me just do an example for you then. If the current altimeter setting is 30.12 inches of mercury, and the indicated altitude is equal to 6,000 feet, you would just have to plug that in, because the CAS is going to be 30.12 minus 29.92 and then we're going to multiply whatever that ends up being by 1,000, which that is actually going to end up being zero 0.2 inches of mercury. So you multiply that by 1,000 to get 200 feet. And then you go ahead and take it from the indicated altitude. So the indicated altitude is 6,000. This time we're going to be subtracting it, giving us 5,800 feet. I made a little bit more of a mess than I was expecting to, so I'm going to go ahead and erase that. If you want to look at it, just go ahead and take a screenshot of this, and I'm going to be back in a second. Finally, you have density altitude, which is just going to be dA, which is just pressure altitude corrected for non-standard temperature variations. Remember that. It represents the density of the air in relation to the standard atmosphere. It is used to assess aircraft performance as it affects engine power and aircraft lift. So it is the most important one, and you're going to have to go through all of that to figure it out. For exams, or if someone throws an EMP into your airplane, you will need to know how to calculate these without a phone or calculator. That being said, once you pass your exams and you make sure no one brings any EMPs onto any of your flights, for flights, the app does it for you. Until then, here are your choices. You can memorize this equation. You can use this graph, that graph as well, or you can use an E6B calculator. Later, I'll show you how to use an E6B calculator for the flight planning video, but today I will be explaining how to use the graph since it is quicker and you have to learn it anyways for your exam. Sweet, now give me a second while I go grab it. Look at this little density altitude chart that I found that you guys are going to want to be able to use. So first off, we can see that it's not like a normal graph that we would normally use. The output is on where the y-axis should be, and the input is going to be on the X, which is normal, but it's also just going to be in lines all across the page, and then there's a table. What do we do? So first off, let's go ahead and start with just noticing that the pressure altitude, that's where we need to start off. We need to finish through all of the example that we went through earlier just to find that right there. We could see that there's a big old line for standard temperature. We could actually use that for an example. Let's go ahead and use the standard temperature, which is just going to be a little bit over 60. Let me just make, yep, actually it is going to be a little bit lower than 60. So 59 degrees Fahrenheit, which we could use Fahrenheit. See that right there? Fahrenheit's right there. And let's just say pressure altitude is going to be 5,000 feet exactly. So we literally just take the 5,000 right there, which is the pressure altitude. That's going to be our input. We're going to see the 59, and we're just going to follow a line up here. And once they cross, you go directly to the left. And as long as this line is basically straight, oh man, with standard temperature, basically pressure altitude is approximately equal to density altitude. And that is also assuming a normal altimeter setting of 29.92, which is the standard, and there's no line for that. If it was non-standard, let's just say an easy one, 28.8 even, we would be adding 1,000 feet, so the density altitude would actually be 6,000 feet. Does that make sense? Let me know in the comments if I did all right at explaining this. Let's do another example. Let's say that the pressure altitude is 2,000 feet. Let's also say that the temperature is 100 degrees Fahrenheit. Why not? All we're gonna have to do is follow about a parallel line, let's go ahead and see, all the way to 2,000. There we go. And all we have to do is track that all the way straight to this. And what do you know? If you have a pressure altitude of 2,000 already, and you have a temperature of 100 degrees Fahrenheit, you're gonna end up, as long as the altimeter setting is 29.92, the density altitude is equal to approximately 4,000 feet. Look at that. TFIs fact check me later. Awesome. Sweet, we went through that graph, and congratulations, you don't actually have to memorize that equation at all. Look at you. already done. And now you have density altitude. Really quick, while I have you here, I'm going to give you a little bit of a life lesson. If you are on the ground and there is no air traffic control or ATIS, you can actually work backwards by getting the elevation of the airport you're at, which you should always know, and you could work backwards to find your altimeter setting. All you have to do is know your altitude, adjust the knob to read that altitude, and congratulations, you have the altimeter setting. Bam, magic, absolute magic. If you learn nothing, you know that. Actually, you should know all of this stuff, but there we go. Now that we have 5 out of the 6 pieces to the 6-pack now, let's just move on to the last part. Let's go. The last part of the 6-pack is the airspeed indicator. And I'm going to be so honest with you. I tried to make this. Oh man, it did not work out very well. So I'm just gonna be using this. There we go. It is the airspeed indicator, and it works by comparing the ram air. I tried drawing that too, right there. It compares the ram air from the pitot tube to the static air from the static port using a diaphragm like other Pitot-Static instruments. Since it uses both systems in conjunction, if either one gets clogged, then there will be issues. If the pitot tube gets clogged, then the airspeed will read 0 because all the air pressure will leak out the drain hole in the pitot tube. If the pitot tube is completely clogged, then the airspeed indicator will work like an altimeter. It will increase with climb and decrease in a descent. Not very helpful. If the static port is blocked, the altimeter and the vertical speed indicator will get clogged, and the airspeed indicator will read lower than accurate in a climb and higher than accurate in a descent. Not great. Very bad issues. I promise this is the last bad thing I'll say about the airspeed indicator. If your angle of attack is not 0 degrees, then there will be at least a slightly low reading on the airspeed indicator because of all the ram air not getting in. It's more than likely not flowing directly into the pitot tube. Now, with all those disclaimers out of the way, let's learn how to read this and put it to good use. Reading the speed is not too difficult. You can see that on the airspeed indicator on my right, it reads, let's see, 140, let's go, 100, 110, 120, 130, 135 knots. What's really important is knowing what these numbers really mean. The really important numbers are called V speeds, and the really important B speeds are indicated on the airspeed indicator. You'll need to study the POH for your plane's make and model to ensure you know your specific craft's limitations and safe operations. Let's get started with the lowest airspeeds, looking at this figure. The thick white arc connecting the notches indicates the range in which the flaps on this plane can operate. The beginning of this range is designated as VSO and is the power off stalling speed, with the landing gear down and the flaps extended, which is going to be 55 knots on this. The end of the white arc is designated as VFE, as in flaps extended, and is the top speed you are structurally able to fly with the flaps extended, which is 100 knots here. The green arc indicates normal operating range for your airplane. The beginning of the green arc is designated as VS1 and is the power off stalling speed with the landing gear and flaps retracted. The end of the green arc and the beginning of the yellow arc is designated as VNO, as in no, don't go that fast, basically. VNO is the maximum structural cruising speed. Operations above this speed are only allowed in smooth air, as a good gust of wind above this speed can cause permanent damage to the plane. The end of the yellow arc. In the entirety of the red arc, it's really more of a just mark, not an arc. The mark is designated as VNE, also known as never exceed this speed. If you go over the speed, it is significantly likely that you will either lose control of your plane and fall out of the sky, or cause serious structural damage and fall out of the sky. Not very good. The last 3 V speeds you need to specifically remember for your aircraft are not found on the airspeed indicator. That is VA, which is maneuvering speed, which is technically, in this case, anything under the yellow arc. The next one is VX, which is best angle of climb speed. This is the airspeed that provides the greatest gain in altitude over a horizontal distance during a climb. It allows the aircraft to clear obstacles in the shortest distance. And the last one is going to be VY, best rate of climb speed. This is the airspeed that allows the aircraft to achieve the maximum rate of climb per unit of time. It provides the best climb performance in terms of altitude gain over time. And sorry, there was a fourth one, because there is VG, which is the best speed to fly at with no additional power to give you the farthest glide. You use VG in examples like when your engine is out and you are trying to do an emergency land. That happens a lot on your exams. These V-speeds are all measured as indicated airspeeds. That is how fast the ASI, or the airspeed indicator, is indicating how fast it is going through the air. For safe and efficient flights, and more importantly, your exams, you need to know the 4 different types of airspeeds. There's indicated, there is calibrated, there is true, and there is ground speed. Just like there's different altitudes, there are different airspeeds. If you took indicated airspeed and removed all of the mechanical error in the placement of the tubes and any error in the instrument, you would get calibrated airspeed, usually not more than 2 to 3 knots. If you took calibrated airspeed and adjusted for less drag at higher altitudes, you would then have true airspeed. Yes, as you increase in altitude, the air gets thinner. Given thinner air, the airplane experiences less drag. This decrease in drag leads to an increase in airspeed that is not picked up too well by the airspeed indicator, given the drop in air temperature and pressure, all of that. This difference in indicated airspeed and true airspeed is most notable when flying to a high elevation airport like Big Bear Airport at 6,500 feet. And if you were to take true airspeed and account for the wind hitting your airplane, then you would have ground speed, or GS for short. I'll teach you more about how to calculate this on an E6 calculator at the end of the flight planning section, but that's basically, as a crow flies, how fast you're flying according to, like, in reference to the ground. So it goes indicated airspeed, then calibrated airspeed, then you could get true airspeed, and then with true airspeed you can then get ground speed. In the last hour-ish, we have gone over all the instruments and all the systems of the aircraft, including the magnetic, gyroscopic, and pitot-static systems, along with their errors. As promised, in the link below is a handful of questions you may or may not see on an official FAA written exam or a final exam for a particular online course pertaining to these subjects. Thank you so much for watching, and I hope this has been helpful. If it has, leave a like and subscribe, and if it hasn't, leave a mean comment or something. I don't know. Either way, we all wish you blue skies and tailwinds. Thank you so much.